All right, chapter 7. Chapter 7, we're going to be dealing with ratios, proportions, and similarity. So we've dealt a lot with shapes being congruent. This chapter, last chapter, then we dealt with like inequalities, right? Sides or angles were greater than others. This chapter, we're going to be dealing with proportions. Logan, of course. Not today, though. I don't think there's any on your homework today. If there is, it's like one small one. I think there's like one kind of like an explanation type of proof. And so this chapter, it's going to deal more with shapes that are similar. When shapes are similar, they have the same shape, but not necessarily the same size. And we have to have ways to compare those measurements, and that's where we use ratios and proportions. And some of this should honestly be familiar from algebra, but a ratio, so for ratio, the ratio of one number to another is the quotient when the first number is divided by the second. So ratios are basically expressed as fractions very often, right? Like division. Like 2/3, you would, as a ratio, would say 2:3, right? Or 4:5, and that's often written as a fraction. You always are going to write a ratio in simplest form. So if you see something that can be reduced, please reduce it. And it's often used to compare two numbers, right? Two values. You'll see it a lot in like sports with like a batting average or just different comparisons of values. Ratios can also be written in the form A:B, where that A or that colon means 2. So that still says A:B. Also, when it's with this colon type of form, we use that for some extended ratios when we want to compare multiple things. So we can also use the colon strategy if we're comparing 3 or more numbers, such as C, D, and E. And this would be read as C to D to E. So that's the comparison of C to D, D to E, and C to E. But you wouldn't like put a fraction with multiple things stacked on top of each other. So we use the colon format for that. Then we're also going to be dealing with proportions. That's an equation stating that two ratios are equal. So you could have the ratio A to B is equivalent to the ratio C to D. It can also be written in our colon format. So A:B equals C:D. And how you would read a proportion like that is A is to B as C is to D. That's our formal way of reading that. We'll also sometimes see what are called extended proportions. That's when you're, again, comparing multiple values. So A is to B as C is to D as E is to F. And that can obviously go on for as long as you wanted to, just depending on what you're comparing. This will be used a lot if we're comparing maybe the sides of a similar pentagons, right? We would have a lot of different sides to compare, so we would need several different ratios. Ratios and proportions, are those concepts in general reasonably familiar to us? We understand what a ratio is, what a proportion is? Perfect. Okay, so that's really what 7.1 is what is a ratio? How do you write it? Okay, so now what we're going to do is just practice a few different applications here. So is the ratio of A to B always, sometimes, or never equal to the ratio B to A? So what do we think? Take a second and think about that. Would the ratio of A to B always, sometimes, or never be the same as B to A? Julia, you gave me a thumbs down and then changed your mind. What made you change your mind, Julia? Precisely. I really appreciate the sideways thumbs for sometimes. I knew exactly what you meant. That's why having the cameras on is so nice. Yeah, no, this is sometimes. Because you're exactly right. What if it's something that could work as a 1-to-1 ratio? So we're going to say sometimes another thing is really just the absolute values have to be equivalent. You're not going to see a lot of like negatives when we deal with ratios, but potentially if you were comparing like 5 to -5, if you like reduce that fraction, it would be -1, right? But if you took that and you flipped it around, -5 to 5 would still be -1. So sometimes, and I'm just going to like put a little addition here, that the ratios are equal when the absolute value of A equals the absolute value of B. So yeah, basically when A and B are equivalent, it will work. Good. 3 numbers aren't known, but the ratio of the numbers is 1 to 2 to 5. Is it possible that the numbers are, and then I've given us some examples. So we do not know what the actual numbers are, but if we did a comparison of them and possibly had to like reduce it down, right? Because you always want to do a ratio in simplest form. Could these possibly be the numbers? Well, if we have a ratio of 1 to 2 to 5, could the numbers just have been 1, 2, and 5? Sure, absolutely. Why not, right? We can't reduce that at all. So that's a possibility. Could the numbers have been 10, 20, and 50? I see a few yeses. Let's see what Brandon sent me. Yep, I agree. This would also be a yes, because if you take those numbers, write it as a ratio, reduce said ratio, you would divide them all by 10, and you would end up with 1 to 2 to 5. Would 3, 60, and 20 work? No, that one doesn't work. You couldn't really quite reduce that. You could reduce the 3 and the 6, but not the 20. But even if it was something you could reduce, like 3, 6, and 18, right? That wouldn't reduce down quite the same. So this one's a no. And then what about D? X, 2x, and 5. Yeah, that one's also good because this is actually just like the generic version of that ratio. X could be any value, right? You could make X 5, you could make X 7, you could make X 231. And if you put that into your ratio and reduced it down, you would still have 1 to 2 to 5. Good. And then this is just an application of how we can apply an extended ratio. The measures of the 3 angles of a triangle are in the ratio of 2 to 2 to 5. Find the measures of each angle. Now I know that many of you could probably just guess and check this, but I want to show you how to actually write an equation for this. First of all, we know that all 3 of the angles are going to have to add up to be 180, right? This is their ratio. So this isn't saying the actual angle values are 2, 2, and 5. That wouldn't make sense, right? That would only add up to be 9. But this is saying if you compared the 3 angles, wrote them as a ratio, and reduced them, it would be 2, 2, and 5. So how do you think you could set up an equation to figure out what my angles are, potentially, Julia? Exactly, yeah, because that's going to tell us what that multiplier was, right? And then we can go back and figure out what our original angles were. Very good. 2x plus 2x plus 5x equals 180. And again, I know many of you, could probably guess and check this, but just depending on what the numbers are, that could take a while. So this is a nice strategy that'll kind of always work for a problem like this. So combine your like terms. You're going to get 9x equals 180. Divide that out, and x is 20. So x was what your ratio was reduced down by for each one. So then just make sure you don't then forget, like, we know what x is, that's great, but you now need to go and plug that back in to find each individual angle. So remember, your 3 angles at the end should add up to be 180. I'm only reminding you of this because on your chapter 5 test, there were a few people who like found X, but then like forgot to plug it back in on a few things. So you should get 40 degrees, 40 degrees, and 100 degrees. And then obviously at the end, make sure your numbers are logical. If you get things that don't add up to be what they're supposed to be, then you did something silly. Hi, Peyton. You just missed the first few things. But I can always go back up to the notes at the end if you need it, okay? All right. So 7.2. 7.2, now we're going to be dealing a little bit more with proportions and their properties. So 7.2 starts on page 245 if you want to follow in your textbook. So I'm going to use a little bit of color coding with this. If you printed it, you might just have like black ink in your printer, but I did a little color coding with the red here. I might do some more with highlighters. But just a couple definitions. We have in our proportions, we have something called extremes and then means. Extremes are the first and the last terms of a proportion. So if you actually look down at these examples, I highlighted my extremes in red. So A and C are my extremes. The means are then the middle terms of the proportion. So that would be B and D. Okay, so that's just how your book defines them. I probably wouldn't define them as first and last, and then, oh wait, it's because I highlighted some stuff wrong. What did I do here? Sorry guys, my bad. I apologize. I've been making a lot of weird, silly mistakes recently. And yeah, I don't know why. So this should actually be, and you don't have to, obviously, if you printed this out and you print it out in black, just like re-highlight it. If you have A to B equals C to D, that's why I confused myself. The extremes are the first and the last terms of the proportion. So your extremes would be A and D. It's the technology, Logan. No, it's not. This was just me doing this way too late at night. And then for this one, it would obviously be the same thing. You would have your A to B equals C to D. And then in a situation where it's written as a fraction like this, right? Same idea though. Your extremes would be A and D, and then your means are B and C. Oh, this one I had highlighted right. It was just that first one that I did wrong. What's the nope for, Sydney? What did I miss? Did I miss any good chats? Nope, not really, Peyton. No one got too wild. So yeah, I just wrote the first one wrong. Okay, good. I didn't have a complete brain meltdown last night then. Just the first one. So yeah, the first one, it should have been A and D were highlighted, not A and C. That's my bad. So for an example here, if you take a look, if we plug some numbers in, like 6 to 9 and 2 to 3, first of all, those are equivalent ratios, right? If you reduce them all down, don't make me close the chat. Don't make me do it. So we would have, first of all, these are equivalent because 2 to 3 equals 2 to 3, right? And I want you to take a look at something. Take those red numbers and multiply them. Wouldn't that be 18? Take these numbers in black and multiply them. Wouldn't that be 18? Right, so that's kind of, I know, David, your mind is blown. But that's how that works. Could you guys remember back in the day cross multiplication? It's basically what that is, right? If you multiply those, it's going to be equivalent to those multiplied. Julia, yes. Yeah, right now I'm just looking at the, like, showing you where everything is right now. I don't know what you're talking about. It says exactly what I intended it to say. It says AD equals BC. I don't know what you're talking about. Listen, I I make a lot of typos. Okay. I'm not going to lie to you. I don't know if you've realized that at this point in our school year. No, I appreciate it. Just Logan giving me a hard time about the technology. I don't have a cat. I could blame my dogs. It was my dogs. No, I blame myself just being careless late at night. So anyway, means and extremes property. Yeah, so and this is, by the way, guys, this is on page 245 in your book. It's in a little purple box. Okay, so you can look at it on there too. So the means extremes property just tells you a few things that your ratio is equivalent to. A to D would be equivalent to B to C because that's like your cross multiplication, right? But also you can switch some orders around. So I kind of want to take a look. This is where I was going to do a little color coding here. Remember, you have so we have our means or our extremes and then our means. Right, and just sometimes a little bit of that color coding kind of helps you to see where everything is. So if you take the extremes times the extremes, right, it's going to equal the means times the means, obviously. That's just cross multiplication. But you can also switch your orders around and still have them be equivalent. So for example, if I took A over C, that would still be equivalent to B over D, right? You still have your same combination of things. Again, I'm just kind of color coding so you can see where all those are sitting. You can also switch your orders. No, I'm not going to use the rainbow colored marker. You can also switch your order around, right, where B to A equals B to C. Those would still be equivalent. And then you can also do this where you take A plus B over B equals C plus D over D. And again, those would still be equivalent. So there's just a lot of different ways to write it where you would still end up with an equivalent proportion. And then we have another property of proportion. It doesn't have a name, but what it just says is if you have an extended proportion, like A to B is equivalent to C to D is equivalent to C to F, then if you take the sum of A plus C plus E, etc., over the sum of B plus D plus F, etc., it's also then still equivalent to A to B, as well as C to D, as well as E to F. And the reason that happens is because you're adding up a bunch of equivalent proportions. When you reduce that down, it would still be equivalent to your original ratio. And if you're curious about that, you can always plug in some numbers and check. Obviously, plug in things that work, right? Like things that work like 1 to 2 equals 2 to 4 equals 3 to 6, right? And you could kind of plug those in and check how that works. Any questions about means, extremes, or our properties? Okay. So just a couple examples here. So we're going to use the proportion x to y equals 5 to 2 to complete each statement. So if I tell you that we have 5 to y, what do you think that's going to be equivalent to on the other side? Or 5y, sorry, not 5 to y, but 5y would be equivalent to what? Yeah, 2x. Yeah, I would write it in that same order, 2x. Exactly. If I have x plus y over y equals, well, then what would I have to do on the other side? And you can do this in one step or in two steps. But if I take x plus y and I put it over y, what will I have to do on the right? Oh, yeah. Sorry, Braden. But yeah, exactly. I would just have to do 5 plus 2 over 2. But remember, always simplify if you can, right? So that would be 7 over 2 would technically be our simplified answer there. Good. If I change this to 2 over 5, what would be equivalent on the other side? What do we think? 2 to 5, what would be equivalent on the other side? Peyton? Sorry, Brayden. Brayden, what do you think? What was that? Well, right now it's x over y. Yeah, no, that's okay. It'd be y over x. Exactly, you're just switching those. And if I took 5 to y, how would I have to change the other side? If I do 5 to y. 5 to y. 5 to y. Y over 2. Exactly. Thank you, Luke. Y over 2. Good. So we're really just grabbing those things in a different order, right? If I reverse this one, then I reverse the other one. If I grab y with 5, I grab y with 2, or vice versa. Are we okay with that? Okay. Now we're going to find the value of x. This is algebra. Ooh, doing a little algebra review. I saw that some of these were on the homework. I'm sure at least one will show up on your test. And I want to make sure that we remember how to apply our means extremes rule, aka cross multiply. Because sometimes you're gonna need to distribute, and the ones I picked require factoring and systems of equations. So I tried to pick out ones that were a little bit more challenging that we maybe needed a refresher on. So who can refresh our memory? Let's apply our theorem here. How would I go about solving for x in number 2? Peyton, what do you think? Yeah, exactly. And make sure with that you're distributing, right? If you guys automatically right away are like, yeah, I'm going to distribute it in my head, cool, awesome. But if you are worried you might like miss a little distribution step, then I always recommend rewriting it. Like how Peyton said, you're going to technically do 10 times x plus 2 equals x minus 1 times 3x minus 2. And you can always put this 10 in some parentheses too, if you'd like. Because remember, the entire numerator and the entire denominator of each fraction is a quantity, so you want to keep it together and make sure that you distribute. So now we can go through and just do our distribution. On the left here, just remember, you're just distributing a single 10. So that's 10x plus 20. We haven't maybe seen this in a hot minute. Who remembers how to distribute when you have two binomials? Julia? Yeah, we're going to FOIL or double distribution, depending on what your teacher called it. Okay, but yeah, exactly. Julia, help me start to FOIL this. Mm-hmm. Would I need a squared on that one? No, that's okay. Yep, good. 3x squared minus 2x minus 3x plus 2. Somebody else, what should I do from here? Yeah, let's simplify. Let's combine some like terms, right? There's a lot going on. I'm going to go ahead and combine some like terms here on the left. If you guys want to do this, again, combine multiple steps into one, that's totally fine. Do what's comfortable for you. But I'm going to say I have 10x plus 20 equals 3x squared. And then I'm going to combine my like terms here, negative 5x plus 2. What is this leading me in the direction of? How am I going to have to solve this problem? Factoring it. Yes, very good. We have our squared. We are going to have to factor this problem. So what I'm going to do is move everything towards that squared term. I would not move your 3x squared to the left because that's going to make it negative. And then when you're factoring something with a negative in the front, weird things start to happen with your signs. I would always move everything towards that squared. So I'm going to go ahead and move this. Can we use the quadratic formula? Yes, you can absolutely use the quadratic formula instead, if that is what you prefer. However, keep in mind, you are going to have to factor next year in Algebra 2. Mr. Ward will not let you get away with just using the quadratic formula all the time. Sorry. So I am going to leave my 3x squared where it is. I'm going to subtract my 10x and make that a negative 15x, and I'm going to subtract my 20 and make that a negative 18. Now, Julia, for this one, I want you to bear with me with my factoring. Okay, factoring is our friend. So, it is, Sydney, I promise. But we're better off remembering how to factor now than showing up next year not remembering how to factor. So, let's look at this. We have 3x squared minus 15x minus 18, and you look at that and you go, oh my gosh, there's a 3 in the front. What in the world is she doing to us? I don't remember. But do you guys notice anything? There's something you should always check for when there's a number in the front before you start factoring. Peyton? Huh? Exactly, there is a GCF. So anytime there is a number in the front here, anytime your x squared has a number, always see if you can divide that number out. Get smaller numbers if you can. So I'm going to have, and technically here, since we're solving, you could just cancel it out. If you were only being asked to factor this problem, you technically have to hold on to your 3. Okay, but I'm technically going to divide both sides by 3, and that's going to become x squared minus 5x minus 6, and that just became a whole heck of a lot easier to look at, didn't it? So now I'm going to move this over here. I'm going to set up my 2 sets of parentheses. Now, we did really well actually with our factoring problem on the Chapter 5 test. There were just a few of us that made some silly mistakes. And the one on the test was actually tricky because it had a 2 in the front. So you guys had to remember how to guess and check that. Here, remember, just put your x and your x. And then what's going to multiply to be negative 6 and add or subtract to be negative 5? Be careful with this one. Peyton. Oh, sorry, I don't know who was about to say that. Peyton. Which ones did you say? Negative 6 and 1. Let's see. Negative 6 and 1. Negative 6 times 1 is negative 6. Good. Negative 6 plus 1 is negative 5. Very good. Does anyone know why I said to be careful with this one? Well, because of the negatives, and also, too, sometimes people look at this and think 3 and 2. Because 3 and 2 will multiply to be 6, and it will add to be 5, but you won't be able to get the correct signs with 2 and 3. Okay, good. What do I do now? I do not know what's happening in the chat right now. What do I do now? Peyton, is your hand meant to be up, or do you just have it up from before? Well, I have to set these equal to something now. You're maybe thinking going through and multiplying them back together. I don't need to multiply them back together. What do I need to set them equal to? One last step. 0. Yeah, just set them equal to 0. X minus 6 equals 0, so I get 6. and x plus 1 equals 0, so I get negative 1. Now with this one, I'm not dealing with measurements. However, it's still good to make sure that your numbers make sense, because is there a type of number that I'm not allowed to divide by? Yeah, I'm not allowed to divide by 0. So if you plug a number in and you end up with a 0 on the bottom of your fraction, is that going to be a solution? No. But this one, this all looks good. We would end up with 5 over 8 here and 10 over 16 here, so we're all good. Yeah, nothing, we're not getting any weird zeros in the denominator. I turned off the chat because it was getting very not math related. If we can handle it in a little bit, maybe I'll turn it back on. So there are 2 answers there. And I think there's at least one other factoring one, maybe 2 on your homework. So you'll have seen that now. That'll hopefully be helpful. Now we got one more. Find the values of x and y. We got 2 proportions here. Why do we have 2 proportions? Why do we have 2 proportions? Any ideas? Nick, why do we have 2 proportions? We're going to have to make a system. Yeah, you need 2 proportions because there's 2 variables, right? 2 variables means 2 equations, means set up a system. So now what we are going to do, what's kind of nice about one of these as compared to like some of the other systems we've done before, there's really only one way to start this problem, and that's cross multiplying or applying your means extremes theorem, right? You got to cross multiply this so you can get some type of logical equation and then either apply your substitution or your elimination, depending on which way you feel more comfortable doing it. So let's take a look at this top equation. I am going to cross multiply this. So again, make sure this one we don't have, we're just have our numbers, so you won't have to FOIL or anything. But we're going to have 4 times y plus 2 equals 2 times x minus 3. All right, distribute. You got 4y plus 8 equals 2x minus 6. I'm going to leave that like that for right now until we see what the other equation looks like, and then we can decide if we want to go the substitution or elimination route. Do I have you guys so far for this one? Okay. All right. Now let's look at this one. This one, we got a little bit more going on here. So, and by the way, guys, does it really matter if you decide to multiply, you know, from top left to bottom right first or the other way around? Not really. Do what you like. For me, I think it depends on the problem. Sometimes I change it every time. What did I do for this one? I'll keep it consistent. I went from the bottom to the top, but it really doesn't matter. You're going to have 6 times x minus y plus 1 equals 5 times your quantity x plus y minus 1. So that's going to give you 6x minus 6y plus 6 equals 5x plus 5y minus 5. Okay, so we got a lot going on here. Something that I would maybe do, the substitution could maybe work okay with this. Because here, I think we could get the x all by itself, right? But it's really up to you. I'm gonna rearrange these to turn them into like your x term, your y term equals your constant, okay? And then we can go from there. But if you want to set this up for substitution, you totally can. I mean, do you guys have a preference? Logan says, yeah, I agree. Doesn't matter. Kind of depends on the problem, right? So, oh, bye, Luke. Okay, so here, let's take a look. I'm just going to simplify this. I'm going to move that 2x over, make that a negative 2x plus 4y equals, and I'm going to subtract over my 8, make that a negative 14. You could have also rearranged it by moving your 4y over. There's kind of a lot of possibilities with this. There's not just one way to do it. All right, let's rearrange the second one. Let's see what we got here. I'm going to move my 5x over. That's just going to give me an x. I'm going to subtract my 5y over. That's going to give me negative 11y equals, and then I'm going to subtract my 6 over to get negative 11. Oh, maybe substitution would be an okay one here. Because I could turn this into x equals 11y minus 11, right? Do you guys have a preference? Because if we do our elimination, we could also do elimination by multiplying this equation by 2. Anyone? Preference? No preference? What, Peyton? Okay, Peyton votes up. Let's do that because we don't do that way a lot. I feel like I do elimination a lot. That's what I tend to gravitate towards. Okay, so Peyton says substitution. So substitution it is. So let's rearrange this one. I'm going to make this x equals 11y minus 11. So I'm going to take this and I'm going to plug it in for x in this top equation here. So I'm going to get negative 2, and then I'm going to plug in my 11y minus 11 plus 4y equals negative 14. I'm going to do my distributing, negative 22y plus 22 plus 4y equals negative 14. That's going to give us negative 18y equals, why are my signs not working out the way I thought they would? Negative 14 minus. Oh, no, that works out just fine. Okay. So subtract that over to get negative 36. Divide that through to get 2. Worked out to be a nice, pretty number, so we're probably on the right track. And now that I got my y, plug it back in to find your x. Typically, you should plug it back into an original equation. So, I mean, you could plug it back into one of these. I'm always about making your life easier, though. I'm going to plug it back in to this equation here. That's technically breaking the plug it back into an original equation rule, but do you really want to plug it back into one of these proportions? Me neither. But at the end, once you have your two numbers, would it be pretty easy to plug back into one of the proportions and double check, make sure it's good? Yeah, at that point, it should be pretty easy to check. But yeah, I'm all for not having to make your life. This class is already hard enough. Let's not make it even harder by doing silly things. So we're going to have 11 times 2 minus 11. So we got 22 minus 11, and you should get that x is 11. We good? That was almost a homework problem. I decided we'd do it here instead. Yeah, I figured we'd probably need a little bit of a preview with that. I think you guys could muscle through it because it's just algebra, but it's one of those ones that kind of can take forever and you can make a few little silly mistakes. There is one system of equations one on your homework, but it's not quite as wild looking as 40 is. And then you do have, I found the one